Hello students, welcome you all to the session of Solutions of GATE 2022 Fluid Mechanics subject for the branch of Mechanical Engineering. Moving on to the first question. A figure shown a purely convergent nozzle with a steady inviscid compressible flow of an ideal gas with constant thermophysical properties operating under choked condition. The exit plane shown in the figure is located within the nozzle. If the inlet pressure is P0 is increased while keeping the back pressure P back unchanged. Which of the following statement is or true? This is the question. Inlet pressure is P0. Convergent nozzle, obviously pressure will be increasing. This is the exit plane. Mach number at exit plane of the nozzle will remain unchanged at unity. Obviously no, this is wrong. Mach flow rate through the nozzle will remain unchanged. Obviously flow, that is your flow rate will be unchanged. True. Mach number at the exit plane of the nozzle will remain unchanged at unity. Yes, obviously. Mass flow rate through the nozzle will increase. Never ever this happens. So obviously, when you are checking with the Mach number for the pressure at the inlet and the outlet, never ever the mass flow rate will be changed, and Mach number at the exit will also remain unchanged at unity. So the answer is option B and C. Option B and C will be the right answer for the given question. Moving to the next question. Consider steady one-dimensional compressible flow of gas with a diameter of 1 meter. At one location in the pipe, the density and velocities are 1 kg per meter cube and 100 meter per second. At the downstream location in the pipe, the velocity is 170 meter per second. If the pressure drop between the two locations is 10 kilopascal, the force exerted by the gas on the pipe between these two locations is dash Newton. A 750 pi, B 1000 pi, C 3000, D 350 pi square. When we see the question, the given data is, let us consider a pipe of section 1 and a section 2. The diameter is 1 meter. Change in pressure is delta P, which will be 10 kilopascal. 10 kilopascal. He has given the velocity at the inlet is around 100 meter per second. When we apply the equation or balance the pressures, P1 minus P2 into A minus F is equal to m dot into V2 minus V1, right? Pressure drop equation I am taking. So P1 is how much? The pressure difference 10 kilopascal. Kilo is 10 cube. Area pi by 4. D diameter is 1. So pi by 4 d square minus F is equal to m dot rho AV into V2 minus V1. When you simplify this equation, you will get 2500 pi minus F is equal to 1 into pi by 4 d square into 100, and outlet and inlet V2 minus V1 you will be getting around 70, right? 170 minus 100, which is 70. From here find out F. Always keep the value of pi unchanged because the questions are given to you, the options are in the pi value. So answer will be around 750 pi. Option A 750 pi will be the right answer, and the units are Newton. Hope you people have understood this. Area is pi by 4 d square, d is 1 meter, P2 minus P1 is change in pressure 10 kilopascal, and velocity V1 is 100 meter per second, V2 is 170 meter per second. So obviously I have taken it directly 170 minus 100 as 70. So option A will be the right answer for the given question. Moving to the next question. A steady two-dimensional flow field is specified by a stream function psi is equal to kx cube into y, where x and y are in meters and the constant k is 1 meter per minus 2 second inverse, that is 1 by meter square second. The magnitude of acceleration at a point x comma y is 1 meter comma 1 meter is dash meter per second square. Round off to 2 decimal places. Right. When you take the given stream function, he has given psi is equal to kx cube y. The value of k is 1 by meter square second. Now, we know that u is equal to minus dou phi by dou y, stream function equation. V is equal to minus dou psi by dou x. When you take psi equal to kx cube y, differentiate with respect to y, we will get minus k x cube. And here you will get 3k x square y. What is the acceleration equation? Ax, especially for a steady flow without considering the temporal acceleration, we say Ax is u into dou u by dou x plus v into dou u by dou y. U minus k x cube into minus 3k x square, right, plus v 3k x square y into dou u by dou x. What happens? 0. Dou u by dou x I have got it as minus 3k x square. Y with respect to y, obviously it will be 0. No constant there. So 3k square x power 5. This is the value of Ax. Moving to Ay. Acceleration at y direction. U into dou v by dou x plus v into dou v by dou y. That will be minus k x square. Dou v by dou x. Dou v by dou x. What happens? It will be 6 k xy plus 3 k x square y, and it will be 3k x square with respect to y if you differentiate. Now minus k square into point is how much? 1 comma 1. 1 comma 1 will be 6 into x power 4 into y plus 9k square x power 4 into y. Point is 1 comma 1. You will get around minus 6 plus 9, that is 3 meter per second square. Ax is how much? Ax also will be 3 meter per second square, because k is 1, x is also 1. Ay is also 3 meter per second square. Finally, total acceleration is, or resultant is, ax square plus ay square, which will be root 9 plus 9, that is 3 root 2 meter per second square. You will get the value of 4.2426 meter per second square. This is the acceleration of the flow. Rounded up to 2 decimals, 4.2426 meter per second square. From fluid kinematics, the question is from the concept of stream function. Moving to the next question. A solid sphere bead of lead, uniform density of 11,000 kg per meter cube with a diameter of 0.1 mm, shrinks with a constant velocity v in a large stagnant pool of liquid. Dynamic viscosity is 1.1 into 10 power minus 3 kg meter inverse second inverse. The coefficient of drag CD is 24 by Re. Reynolds number Re is defined on the basis of diameter of the bead. The drag force acting on the bead is expressed D equal to CD into 0.5 rho V square into pi d square by 4, where rho is the density of the liquid. Neglecting the buoyancy force, use G equal to 10 meter per second square and velocity is dash meter per second. A 1 by 6, B 1 by 18, C 1 by 24, D 1 by 12. Here given density is 11,000 kg per meter cube. Diameter is 0.1 mm. G is 10 meter per second square. Dynamic viscosity 1.1 into 10 power minus 3 kg per meter second, where he wrote it as kg meter inverse second inverse. And the buoyancy force should be neglected. Now, for example, this is the free surface, this is the ball, right? There will be the weight force and for equilibrium condition what I'll write is weight force is equal to drag force, that is weight rho g into volume pi by 6 d cube is equal to drag, he has given 1 by 2 rho pi by 4 d square into v square. What is the value of CD? 24 by RE. That is V equal to rho g d square by 18 mu you will be getting. Rho g v square by 18 mu, here it is mu, right? On solving the above equation, substitute here 11,000 into 9.81 into 0.1 square by 18 into 1.1 into 10 power minus 3, because he has given 1.1 into 10 power minus 3 g. So he has given take value of g is 10 meter per second square. Okay, accurately we'll take this 9.81, you write it as 10, you write it as 10, solve it, you should get around velocity is 1 by 18 meter per second, right? Drag force, don't get confused, CD 0.5 rho v square into pi d square by 4, right? So this is the value how you will be taking, and you will get the value of 1 by 18, that is option B. Option B will be the right answer. Here mu value was missing, I have taken this as 24 mu by RE, right? This is the solution for the question given. Moving to the next question. By this, we have completed the questions of fluid mechanics. Hope you people have understood. Thank you, students.